Hey kids, welcome to section 4.5 Probability and Counting Rules. Today we're going to put everything together and find the probability of an event using counting rules. So, by using the fundamental counting rule, the permutation rules, and the combination rule, you can compute the probability of outcomes of many experiments. So, for example, if I want to find the probability of getting four aces when five cards are drawn from an ordinary deck of cards, well, now we're going to be finding probability. So, the practicing that we did in the previous section with finding the number of outcomes, that's going to go on the bottom. And then on the top of the fraction for probability, we're going to find the probability of that actually happening. So remember, probability is always total outcomes on the bottom, and the specific event is going to go on the top. So in this situation, we're finding the probability of getting four aces when five cards are drawn. So the total number of outcomes on the bottom is 52 cards. Choose five. Because it doesn't matter what order I pick these cards in, I'm just picking five cards. Now, out of all those five cards I chose from 52, I want them to be very specific. I want to get four aces. Well, there's four aces in the deck, and I want to choose all four of them. And then I have one more card that I can draw to get my fifth card. So there are 48 other cards in the deck that I can choose one from. Then I multiply those events together. So basically, it's like three little combination problems in one. This four choose four kids is your aces. Your 48 choose one is going to be your other card. And the 52 choose five is the total picking. That's not very proper, but we'll go with it. So on the top, four choose four is one. It's kind of weird. If your N is the same as your R, then the answer is always going to be one. And then 48 choose one is 48. That's another weird thing, that if you have N choose one, the answer is just N. And then on the bottom, there are 2,598,960 different ways you can pick five cards. If we do this on the test decimal, we're going to have to do some weird rounding, kids. There's one, two, three, four, two. This is going to be one of those situations where you're going to have to get a first non-zero number on the calculator. All right, let's try another one. A store has 6 TV graphic magazines and 8 news time magazines on the counter. If 2 customers purchased a magazine, find the probability that one of each magazine was purchased. All right, so total number of outcomes goes on the bottom. What's happening? Well, there's 14 magazines and 2 of them are being bought. So that's 14 choose 2 on the bottom. Doesn't matter what order they were bought in, just matters if they were bought. Now it specifically says you want one of each. So that means out of the 6 TV graphic magazines, you're going to choose one. And out of the 8 news time magazines, you're going to choose one. And then we multiply those together. Let me mention another thing, kids. This 6 and the 8 on top should always add to the 14 on the bottom. The left number and the bottom left number equal the bottom left number. Same thing with the right numbers. The bottom right 1 and the bottom right 1 add together to get 2. It worked in the previous one. Left 4, left 48 add together to get 52. Right 4, right 1 add together to get 5. That is always true. Always. So 6C1 or 6 choose 1 is 6. 8C1 or 8 choose 1 is 8. And on the bottom, 14 choose 2 is 91. So that's going to give us 48 over 91, which is 0.527. So it's kind of a 50-50 shot if one of each is going to sell or one of each is not going to sell. All right. Let's do some more defective transistors. All right, so we got a box contains 24 transistors, 4 of which are defective. If 4 are sold at random, find the probabilities. Okay, so exactly 2 are defective. All right, so we have a box of 24 and we're picking 4. All right. Now, it doesn't matter the order that these are chosen in, we're just grabbing them. So on the bottom is going to go total possibilities. Well, there's 24 transistors and we're choosing 4 of them. On the top, well, I only want 2 that are defective. So that means out of the 4 defective ones, I want to choose 2. Now that means I have 20 other transistors to choose my other 2 from. So the other part of the top is 20, choose 2. So on the left side is the defective ones, on the right side is the non-defective ones, and on the bottom is the total. So if I do this, I get 6 times 190 on the top, and I get 10,626 on the bottom. So the numerator is 1,140. The bottom is 10,626. And if we divide, we get 0.107. So if there's 24 transistors, 4 of them are defective, and I stick my hand in a bag and I grab 4 of them, 2 being defective is going to happen about 11% of the time. All right, how about the fact that none are defective? Okay, well, that means I still have 24C4 on the bottom because I'm still grabbing 4 from the box of 24. Now I don't want any defective ones. So that means from the 4 defective ones, I don't want any. So 4 choose 0. And then from the 20 non-defective ones, I'm going to pull all 4. So 20 choose 4. So on the top, I have 1 times 4,845. In the denominator, I have 10,626. So that gives me 4,845 on top, 10,626 on the bottom. I divide, that gives me 0.456. So roughly a 46% chance that if I grab 4 transistors, none of them are defective. It's not very good odds. Okay, what's the probability that all of them are defective? Okay, well, we still have 24 transistors in the box and we're still choosing 4 of them. From the 4 defective ones, I'm going to choose 4. And from the non-defective ones, I'm going to choose none. So 4 choose 4 times 20 choose 0. All over 24 choose 4 number of possibilities. Okay, on top, I have 1 times 1. 4 choose 4 is 1. 20 choose 0 is 1. Kind of weird pattern that happens there. And on the bottom, I have 10,626. Kids, there is only one way to choose 4 batteries and have them all be defective. And that's a 0.00009 chance. Pretty small chance that the 4 transistors you choose are the 4 defective ones. Okay, probability that at least one is defective. Ooh, we love these. So the probability of at least one defective, remember what we do with at least, that's equal to 1 minus the probability of no defectives. Okay, well, 1 minus, what's the probability that there are no defectives? Well, we just found that up here in letter B, 0.456. So I'm going to put 1 minus 0.456. and that's 0.544. So use what they make you do. All right. In the Pennsylvania State Lottery, a person selects a 3-digit number and repetitions are permitted. If a winning number is selected, find the probability that it will have all 3 digits the same. All right, well, let's think about these a slightly different way if you want to. We're still doing probability, we still got to do total outcomes on the bottom. Well, if we have a 3-digit number and repetitions are permitted, 3-digit number, repetitions are permitted, then I have 10 to the third or 1,000 different ways that I can do that. So my bottom number is 1,000. On the top, I have to, on the top, there are 10 different choices for the first one. But if all 3 digits are the same, there's only one choice for the second, and there's only one choice from the third. Because whatever I choose for the first, I have to use the same thing for the other two. So this is 10 over 1,000, which is 0.010. Okay, on the bottom, there are 8 married couples in a tennis club. If one man and one woman are selected at random to plan the summer tournament, find the probability that they are married to each other. Well, total number of possibilities. I got 8 men and I got 8 women. So there are 8 times 8 different possibilities for the men and women to be married. On the top, there are 8 ways that they could be married to each other because they're already married. So there are 8 ways they can pair up. That leaves me with only 1 out of 8 ways that they can be married to each other, and that's 0.125. All right. Application. One of the biggest problems for students when doing probability problems is to decide which formula or formulas to use. Another problem is to decide whether 2 events are independent or dependent. Use the following problems to help develop a better understanding of these concepts. So assume you are given a 5-question multiple choice quiz. Each question has 5 possible answers, A, B, C, D, and E. How many events are there? Well, events are things that are happening. Since there are 5 questions, there are 5 events. And we'll put 1 for each question. Okay, number 2, are the events independent or dependent? These events are independent. It does not matter what you chose for question 1. That should not influence what you choose for question 2. Okay, number 3, if you guess at each question, what is the probability that you get them all right? Well, there are 5 choices for each question, and there's only one right answer. So you have a 1/5 probability of getting the question correct. But since they're all independent, I can multiply it by itself 5 times for each of the 5 questions. So 1/5 to the 5th power. That gives me 0.0003. It's pretty small that you'll get them all right if you just guess. What is the probability that a person guesses answer A for each question? Well, that means that they have 5 choices to choose from, and there is only one way they can choose choice A. And there are 5 questions, so it's to the 5th power, so 0.0003. Okay, now let's change it up a little bit. Assume that you're given a 5-question matching test in which you are to match the correct answers in the right column with the questions in the left column. You can use each answer only once. Well, how many events are there? There are still 5 events, 1 for each question. Are the events independent or dependent? These are dependent events. The answer to number 2 depends on what I answered to number 1. And what I answer for number 3 depends on what I answered for the other 2. So they influence each other, so they are dependent. All right, number 7, what is the probability of getting them all correct if you are guessing? Well, if you're guessing and you're, matching them up, you have a 1 out of 5 chance of getting the first one right. But the second question, you only have 4 choices left and only 1 is right. The third question, there's only 1 right choice out of 3. The second to last question, there's 1 out of 2, and the last possibility is only 1 to 1. If I multiply this, I get 1 over 120, and that's 0.008. And then finally, what is the difference between the two problems? The first problem is with replacement. The second problem is without. So the first problem, so that would be numbers 1 through 4, is with replacement. The second problem, that would be 5 through 7, is without replacement. All right, so super important difference. In the first question, each problem was independent or with replacement. And the second question, the choices were dependent. And so you had without. All right, kids, that's the end of section 4.5. If you guys have any questions, let me know. And as always, keep calm and keep trucking.